So today I'm not going to use slides, not much. All right, so most of the time I'm going to write on the whiteboard because in the previous class, what we introduced the Gauss's law, right? Which is this. Essentially, on the left-hand side, we had flux, electric flux, and then charges enclosed within the whatever chosen Gaussian surface. So now let's look at a few examples. Again, as I said, the problem with the Gauss's law, that it's great, it's elegant, and so on, and most of the time we use it to find the electric field, right? But the electric field is inside of the sign of integration, so somehow every time if you want to find the electric field, you need to extract it from that integral. And as I told you, good luck with that, because most of the time it can be ridiculously complicated. Unless you have a nice symmetrical distribution of charges. If, for example, you have, that's what I'm going to start. If you have a sphere uniformly charged, then application of the Gauss's law, it's very, very simple. If you have a cylinder infinitely large, charged, again, application of the Gauss's law is very simple. So today we're going to look at this example and that example. Right? So pretty much the whole class, it will be just examples of the Gauss's law. OK, so now let me start with more than art. I will try to draw a sphere. OK, not bad for morning, for 8 a.m. or 9 a.m. class. I expected worse. So let's assume that this is our sphere. You see, uniformly charged. Let's assume it's positively charged for simplicity. All right, so let me draw a few pluses. All right, so plus, 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 plus. All right, OK, enough. And radius r. Right. So charged object, there must be an electric field around that. So, and what is given, I wrote, nothing else. And so what needs to be found? So let me write in part A, let's say part A, we need to find electric field. Let's start with outside. When r is larger or equal than r capital. So outside. And so now, again, guys, if something not clear in terms of my handwriting, I know. Just tell me what is not clear. For me, everything is clear. So how many methods do we have now to solve this problem? The hint is 2, right? So the way like we integrated that ring a couple of classes ago, pretty much Coulomb's law with a probe charge, that's the first method. And now Gauss's law. If you try to apply the first method, again, it's durable. You can finish integration, but it will be significantly more complicated. So which methods to use, this or that, it depends on the problem. Sometimes Gauss's law is easier, sometimes that Coulomb's law is easier, right? So it depends on the situation, right? Depends on the symmetry and so on. So here we're going to use, of course, Gauss's law. So let me, it's a good habit, of course, to show what you're planning to use. Right, so that's our just a general law. And so now let's start applying it. So first of all, what do we have to, what should be the first step in applying Gauss's law? Without that step, we wouldn't be able to move any further. So what's the first step? Can you guess? OK, not guess. I know. Do you see? Find what?
Do we want to find the flux first?
Flux, of course, at some point we will have to find, and probably I will do it one of the first things. But even before we start finding flux, flux through what? Of course, you're looking at me, it's obviously through some surface, right? Yeah. Yeah, that's which surface?
Outside? I don't know.
Surface. we haven't picked the Gaussian surface. So what you said is absolutely correct. But before you can start finding flux, or before you can start finding Q enclosed, everything depends on your choice of Gaussian surface. So the first step, whenever you want to apply Gauss's law, first step must be you have to pick a Gaussian surface. Because otherwise, integration over the Gaussian surface, if you didn't pick it, come on, there's nothing to discuss. Q enclosed also, charges within the Gaussian surface. If you didn't pick it, again, there's no question. So then, as I told you in the previous class, Gauss's law can be applied for any closed surface, which we call Gaussian surface, right? Any, literally, I can pick this surface, I can pick over there some crazy looking surface, but it must be a closed one. There is only one restriction, it must be closed. But where that surface, which shape, it doesn't matter. It's legitimate to apply Gauss's law, right? Okay, so first step, we need to pick a Gaussian surface. Let me even write, so we need to Gaussian surface. Okay, great. So now, where should that Gaussian surface be? Essentially, look, in the Gauss's law, electric field on the Gaussian surface. So since we want to find the electric field, of course, our electric field outside, so Gaussian surface must be outside. Because essentially, we probe the electric field on the Gaussian surface. If we want to find the electric field outside, of course, the Gaussian surface must be outside. It's like, it would be silly to try to probe, I don't know, the life of Canada by going to some country in Africa, for example, because life's completely different, right? So you need to go to that particular country in order to explore that life. Here the same. We're interested in life over here, so we need to pick the Gaussian surface over there, right? Okay, so now, great. So now we know where the surface should be. Shape. Which shape? Again, as I told you before, you have universal or constitutional freedom to pick any shape you want. Literally any shape. And if you pick, I don't know, the shape in the form of the heart, I don't know, right? Three-dimensional heart, it would be correct. I would never be able to tell you that you are wrong. But the thing is, if you pick that shape, you will never be able to solve the problem. Okay, maybe with tons of efforts, right? So sometimes being correct is not enough, right? So you need to be wise, and you need to pick the best possible surface, because you have freedom, you have tons of freedom, you can pick any surface. Why would you pick a crazy looking surface? Of course you will try to pick the best surface so that you can use the symmetry. We have symmetry, spherical symmetry of the problem. So we need to pick the best possible surface so that we can utilize the symmetry. And of course you can easily guess what will be the shape of the surface? Sphere. Sphere, right? Of course, we're looking at basically cross-section, but of course you need to remember every time that it's a three-dimensional situation, right? So we need to pick a sphere, which would have a radius larger than r capital, right? Okay, so I usually use dash line, green. Of some arbitrary radius r. Basically, r small, it's a variable because we're going to get electric field as a function of distance from the center. So r is just a sum arbitrary between infinity and r capital. So essentially, we're going to have a function, electric field as a function of r. Great, so that is our Gaussian surface. So now next, now we have a Gaussian surface, and now we can start either evaluating Q enclosed or flux. Okay, Owen suggested to start with the flux, so let's do with flux. All right, so I will write, so integral of E dot dA. So I'm starting with flux. And again, it's a surface integral. It's not trivial. But we will take care of that without taking the integral, actually. So in order to simplify it, first step, let's draw electric field vector and area vector on our picture. And let's start with the area vector. And quite often I see students drawing this area vector, for example, attached to this physical surface. Strictly speaking, it's not completely wrong, but it's also kind of not right, because this area vector belongs to what? To the Gaussian surface. So area vector should be drawn next to the Gaussian surface, right? So then, area vector, you remember, by definition, it must be perpendicular to the surface. And the convention, just before we started introducing Gauss's law, you remember which convention we imposed? That the area vector must point towards the outside, right? Of course, when the surface is open, you can pick any direction, but here we impose that convention. Okay, so perpendicular and towards the outside, it means that area vector, for example, if I take that patch, it must be radial. Perpendicular, so this angle is 90 degrees, and towards the outside. Over here, I can also draw, if I take this patch, so this will be my dA. I can draw it also here, over here somewhere. So it's radial. Okay, great. Now, what about electric field vector? Can you guess what's the direction of the electric field because of the symmetry? Kind of guts feeling?
Just outward.
Basically, you mean radial also. Yeah. But let me justify it. Basically, he said that electric field will also have the same direction. For example, electric field vector will be like this, like that, so I can draw as many as I want. But let me justify it. Maybe I will draw it over here. A justification that the electric field is radial. Okay, so this is my charged sphere, right? And let's say I want to find, I don't know, electric field at this point. And this is the center, this is the line connecting them. So, since it's a uniformly charged sphere, of course I can, for example, over here, I can find some point charge. I can take some point charge. Charges are everywhere. So at that particular point, I can take a small point charge, right? And so what will be the contribution to the net electric field at this point? Point charge, of course it will be this way, right? So you remember, like, if you have a point charge, electric field lines are like this, right? So I'm just drawing one of these lines which goes through this point in question. So nothing fancy. So this will be E green. But then at the same time, since it's a uniformly charged sphere, I can find symmetrically positioned point charge over here, because again, it's uniformly charged. So we can find charges at any point. So, and of course, what will be the contribution from that point charge? It will be this. Exactly the same in magnitude, but of course, direction will be that one. So now look, if I add these two vectors, principle of superposition, of course, the net electric field will be pure radial. So pretty much during your integration, for any charge over here, you can find symmetrically charged over there. Tangential components cancel, and only radial components are going to survive, right? So pretty much, but usually in the books, books says it's obviously because of the symmetry, the electric field is going to be radial as well. Okay? So of course, on the exam, I will never ask you to justify if you show me the correct direction of the electric field, I can buy it, right? So, okay, so now let me draw next to these dAs our electric field. Of course, I can draw them everywhere, but I just don't want to make our picture more complicated because we're going to draw a lot on this picture. So I'm just going to draw next to our area vector because that's what we're interested. We are interested in their mutual orientation. Over here, I can draw electric field. Over here also. All right. Okay, so enough. So you see, they are parallel to each other. At any point on the Gaussian surface, they are parallel to each other. Okay, so now let me open my explanation box. All right, and show that on our Gaussian surface, electric field is parallel to dA at every point. Right? And so, of course, now we can take care of a dot product. We remember the definition of the dot product, right? So now let me write it explicitly. So it's a E dot dA. It's E times dA times cosine. Which angle? What's the value of the angle? Angle between what and what? You see? Between E and dA. What's the angle between them? 0. Okay. Because sometimes I see, or actually quite often, students kind of not comfortable with that. That's why I paused and started bugging you. Right? So 0 degrees. 0 degrees. So cosine of 0 degrees is 1. As a result, we're getting that this dot product is just the product of absolute values of the electric field and the area vector. So let me rewrite our integral. It might look for you almost like the same. They're not the same. Here we have a product of two vectors. Here we were dealing with vectors. Now it's just a product of magnitudes. Now it looks like we don't care about the directions anymore. Now it's just a magnitude of E, magnitude of dA. It's a significant step. We managed to get rid of vectors. Okay, and now the next step, again, I will open my explanation box. And now let's try to use the symmetry. So far, so good. I'm trying to make small steps. All right. But again, if something is not clear, tell me immediately. Okay, so now, imagine yourself sitting, for example, at this point. And let's say you know the value of the electric field. Let's say, I don't know, 5 newtons per coulomb. I'm just making it up. So, and of course, this electric field is created by what? By this distribution of charges. You can look down, you can see this distribution of charges. And you know 5 newtons per coulomb was created by that distribution of charges. You remember that, or maybe you took a picture. And now let's say you move to this point. From that point to this point with that photograph. And now if you look down at the distribution of charges, will it be exactly the same distribution of charges? Of course, it will be exactly the same. You will never be able to tell, to see any difference. So if the distribution of charge is exactly the same, what can you say about the magnitude of the electric field at that point? It must be also exactly the same. It must be exactly the same. Of course, direction is different. This direction this way, that way, but we don't care about the direction anymore. We have magnitude. So we only care about the direction of the electric field. Okay, so, or you can move to this point or any point on the Gaussian surface, and you can say exactly the same words. You can say immediately that electric field magnitude on the Gaussian surface is exactly the same at any point, constant. So over here I can write E equals constant on the Gaussian surface. Okay, sometimes I see students making this statement on tests. They write electric field is uniform. It's not uniform. It's just because of the symmetry and because we were wise and we picked the best possible surface, electric field is constant on the Gaussian surface. But if you step away from the Gaussian surface, for example, if you move closer, what happens to the electric field? It gets stronger because you're closer to the source. If you move farther away, of course, electric field gets smaller, right? So electric field is not uniform. It's just constant on our Gaussian surface because we picked it the best surface possible. Okay, so electric field is constant, and as a result, what can be done with any constant factor inside of the integral? Extraction. And you remember, good luck usually with the extraction of the electric field from the sign of integration. But in this case, because the problem is nice and symmetrical, extraction is quite straightforward and quite simple. So we can extract it. And so 2 steps. Before the extraction, 1 step, I don't know, like anesthesia, right? So first you anesthetize, I don't know, like in dental work, and then you do actual extraction of the tooth, right? So now we could extract it, and we can write, so it's electric field times the integral over our Gaussian surface of dA. Okay, and you remember we discussed the value of the integral when, you remember we integrated over a ring. And I was bugging you. So what's the value of the integral? What's the value of the integral? And you eventually told me it was circumference of the ring, right? So now, what's the value of this integral? Of that integral? Okay, again, guys, you need to remember that we're still, I cannot draw three-dimensional pictures all the time. I'm not fancy software, right? I'm just a human being, right? So it's a basically cross-section. It's a three-dimensional object. So it's a? Okay, in words.
I don't know.
It's a area of the sphere. It's an area of the sphere. Because what is essentially, okay, I didn't take that ball. Oh, maybe did I? Let me check. Oh, yeah, I did take. So what is essentially this integral? So it's a dA, it's a small patch, area of the small patch. Then, again, integration is just a fancy word for adding small, in this case, small areas. So dA plus dA plus dA plus 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 plus, and you keep adding those small dAs until you finish, until you cover the whole sphere. So once you finish adding them, what are you going to get? Just the area of the whole sphere. Area of the sphere, Gaussian surface. And we know the answer. It's a 4 pi r squared. 4 pi r squared. So you see, we're basically using high school knowledge because still, in order to use rules of calculus 3 to integrate this, we will have to still maybe spend like 5-10 minutes taking this integral carefully. But we know the answer. So we're going to use that in this class because some of you still didn't take calculus 3. Okay, so it's a 4 pi. And be careful with r's, because quite often on the test I see students you use different r's, r small, r capital, so whatever is nearest. In this case, it's a, which r? Small, be careful guys, because it's the area of the Gaussian surface. In this integral, we are on the Gaussian surface. We are not moving away from that Gaussian surface. So in this integral, it's the area of the Gaussian surface, 4 pi r small squared, because integration over this particular surface. Right. Okay, so as a result, our flux, again, it's a number of electric field lines crossing our Gaussian surface. That's the value of the flux. So now we found your flux, which you wanted to find in the first place. Okay, great. So we took care of the left-hand side. Now, according to the Gauss's law, it must be equal to Q enclosed over epsilon naught. So that's what we have now. Okay, and so now Q enclosed. So what can you say about Q enclosed? Yeah, we basically need to look at all the charges inside of the Gaussian surface. So can you see what's the value of the Q enclosed? Again, it's a physical meaning. It's the total charge which is physically present inside of our Gaussian surface. Where the charge inside of the Gaussian surface, we don't care, as long as it is inside. So what's the total charge inside of the Gaussian surface? Do we know that number? Okay, not number. Do we know that? Because we don't have numbers, we have symbols. Do you see it? What is that? Say it again? No, there are no numbers, but we have symbols. In terms of our symbols, what's the value of the Q enclosed? I see your hand. Q capital, right? Yeah, it's a total charge. It's a total charge, right? So it's just this whole charge is inside of our Gaussian surface. Of course, Q enclosed in this case is trivial, right? So it's just Q. Okay, so now instead of this, we need to replace this with Q. Never leave this subscript in your answer, because essentially it means that you haven't finished the problem. Right? So as a result, we're going to get from here E equals 4 pi r squared goes there, downstairs, so it will be 1 over 4 pi epsilon naught q over r squared. So that's our function. And again, it's only correct for the outside, when we are outside. And it's a function of r. R is the variable, which can change from r capital all the way to infinity. Maybe I should even write so. And less than infinity. Right.
That's the final answer.
Huh?
That's the final answer.
Yeah, it's a final answer. It's a function. Because you remember, we introduced r essentially as a variable. It was completely arbitrary radius, right? So which can be between r capital and infinity.
Add numbers, we just plug in the numbers when we
Yeah, so we assumed essentially q capital is given, r capital is given. So constant, universal constant, it's a given number, and the variable, because it's a function. So function of r. So it decays as 1 over r squared. Okay, you see, it's not that complicated, but there is a part B, and I will show you where most of the mistakes students make usually. Okay, done. Okay, I will put a happy face. And I remember when I was a student, we liked these problems because they are very well organized. Once you understand the idea, it's pretty much like almost becomes mechanical. Right. Okay, any questions so far? Okay, good. So now part B. Let's find the electric field inside. So now we need to find electric field when R, okay, let me write like over here, inside, and then when R is less or equal than R capital. And of course, there will be again Gauss's law. And new problem essentially, different region, essentially it's a new problem. And again, we need to start with what? With choosing a new Gaussian surface. For each problem, we need to pick a new Gaussian surface because again, we're interested in the electric field in a different region. And of course, we sort of probe the electric field with the help of our Gaussian surface. Of course, Gaussian surface must be also different. Wait, my ball is so full. Okay, I will take care of that later. So again, it must be now inside. Again, you can pick any surface, but we need to pick the best possible surface. And of course, you can easily guess it should be a sphere. Again, sphere, but now position inside. So that's the Gaussian surface for part B. Again, of some arbitrary radius r. R small, it's our variable. So now this is for part B. For part B. Right? And let me ask you, what will be different for part B, for this part? Are we going to see any differences if we are going to try to calculate electric flux for part B relative to part A? It will be, everything will be exactly the same. Area vector will be still out, electric field still radial, right? So then, so this step will be exactly the same because they will be parallel. Then again, because we pick the best possible surface again, we can use the symmetry again, we can extract electric field. Then again, electric field is constant. So from this point all the way to this point, everything is going to be exactly the same. So of course, if you want to practice, you can repeat it one more time, but of course, I'm not going to do it, right? So I'm going to write just exactly the same steps, and I will write this part. Okay, so, but of course, I will show you still electric field at a few points, right? So maybe over here also electric field. Then area vector also, I can show it on this picture. I mean on this surface, dA, and over here also dA, and so then exactly the same steps. So using exactly the same steps, okay, so we can write, I will just write immediately this. So E times 4 pi r squared equals to Q enclosed over epsilon naught. And of course, if you see on the test problem which consists of two parts, like this inside and outside, you can use the same, right? So there is no point of wasting your time and repeating exactly the same steps, right? Okay, so now we evaluated the flux, and now Q enclosed. And this is the fun part. And this is where usually only maybe like 30% of students could manage to complete this part, although there is nothing complicated. It's still, you remember that slide about charge densities, which we discussed a couple of lectures ago. We still need to use exactly the same formulas. But now it's for three-dimensional situation. So first of all, let's see on a picture where Q enclosed R is. Again, it's an all total charge physically present. So this is our Gaussian surface. So our Q enclosed is here only. This charge will be outside. This charge will be outside. So we're not supposed to include them. So our Q enclosed is over here. Let me highlight it like this. So that's our Q enclosed for part B. We need to calculate only this amount of charge. Any charge outside, that's outside, which we're not supposed to count, right? And so it's obviously going to be smaller than Q capital, right? So, and essentially we just need to apply the formulas which again we discussed a couple of lectures ago. You remember for three-dimensional case, volume charge density. Can we find volume charge density for three-dimensional case? Yeah, I also believe so. So how? For example, here's the ball, right? So let's say about mass density. So how can we find mass density of this, for example? Uniformly, mass is uniformly distributed. Let's say we know total mass, let's say 5 kilograms, and volume 2 cubic meters. You shouldn't guess. You should say immediately the answer.
Okay, so you find the volume of
yeah.
That's the volume of the but they still.
Okay, you're trying to see the answer immediately. Okay, I'm trying to divide it into steps. So first, yeah, you're trying to write down the answer immediately. So everything that we need to know for this part is here in the definition of the volume charge density, Q divided by V. So first, let's find the volume charge density of our dielectric charge sphere. By the definition, total charge Q is given, our radius is given, so we can easily calculate the volume, right? So rho equals Q divided by the volume with radius r capital, of the sphere with radius r capital, our physical sphere. Because right now we're not on the Gaussian surface, we just want to find the volume charge density. And of course, another mistake students quite often do on the exams, they just don't remember the formulas for the volumes. So sometimes I can see students use the area of the sphere and so on. Usually on the formula sheet, at the end of the formula sheet, I already created the list of those formulas. So just be careful. Don't use the wrong formulas. It's just, for your level, guys, you shouldn't be making those mistakes, right? So anyway, it's a 4 pi over 3 r to the power of 3. So that's the volume charge density. Density of over here. And so now, how can we find Q enclosed? So essentially, it's the amount of charge in smaller portion of the sphere, of our sphere. Essentially, we can look back to this formula. So now we're interested in the charge. So we just need to solve this formula for Q. Q, it's a rho times V. Rho we found, but now volume of the where Q enclosed is. So essentially, I apply first this formula for total charge Q. I can write it like this. And now I want to apply the same formula, but now for, let's say, Q enclosed over the volume of R small. So exactly the same formula I could apply first for the total charge and then for Q enclosed. We have uniform charge distribution. Rho is exactly the same. So first we use this formula to find rho, and now since now we found rho, we can use it to find Q enclosed. Q enclosed, it's a rho times that. So rho times volume of the sphere with radius r small, which is the volume of the Gaussian surface. Volume of the Gaussian sphere, right? Okay, usually I present it in this way. So of course now you can plug it. So this, so you will get Q over V R capital times V R small. Oh yeah, I use this, right? And now it will be charge times the ratio of the volumes. So it will be Q 4 pi over 3 r small cube over 4 pi over 3 r capital to the power of 3. So this factor can be cancelled, of course, right? And we're getting charge times ratio of these cubes. So in this part of the problem, tons of usually mistakes. Right? I know usually like 30 or 40% of students could actually usually manage to get through this part. Right? Sometimes students just memorize and write this answer. If but of course, I want to show the. Sometimes some students find it's easier to understand. Basically, again, since we have uniform charge distribution, so of course we can find volume charge density using this or that. And now since these volumes are the same, I can write it this way. So rho from one side, it's a Q over V R capital, right? And from the other side, it's a Q enclosed over V with R small. So now if you connect these two ends, you will get Q enclosed. Exactly the same like what we have over there. So for some students, when I write it like this, they can, it's easier to understand. Okay, so it's up to you which way. But again, it's just a definition of charge density and some logic only, right? So, okay. Since students struggle with this a lot, I created some additional assignment I will give you, maybe in terms of sort of like an additional kind of homework, but I will think how to arrange it. I will do it next week, right? So, and I will give you tons of different situations where we have to find surface charge density, volume charge density, linear charge density, find the amount of charge here and there and everywhere. Because again, I strongly believe that it's not the place where you should have troubles. Right. Yeah. Never have what?
An
Angle?
Direction.
Direction of what?
Like for the charge or whatever.
You mean the direction of this?
Yeah.
Direction we just discussed using conceptual that?
In other cases,
Okay. In other cases, if you change slightly, if you position here a point charge, it will ruin the whole situation. Because we will lose the symmetry. So for each particular case, we will have to discuss that particular situation, right? So we cannot generalize it. If you have spherical symmetry still in your problem, essentially most of the steps you will just have to repeat. But if you, with some changes, you ruin the symmetry, then good luck with your solution, right? So it will be very, very challenging.
so it's best to just choose a perpendicular like
It's not choosing what?
the charge, like the direction.
No, at this problem, we didn't choose anything. We justify this or that fact. Area vector must be perpendicular by definition. We drew according to the rules. Electric field, because of the symmetry, we sort of justified that it should be radial. We did not choose. We stated the fact, just discussed and stated that on the picture. So it's not our choice, right? We had some choice in terms of direction of area vector, but you remember we removed that option from you. Right? So you don't have any freedom in choosing something. Yeah, you have a freedom in choosing Gaussian surface. You can pick any surface you want, right? So that's the only option. Right? Okay, so now this must be plugged into that expression and finalize the problem. So now let me rewrite it and let me show you that I'm going to just rewrite that. So E times 4 pi r squared equals to q over epsilon naught and the ratio of these cubes. 2 r smalls can be cancelled because they're on both sides, right? You see? So here we'll have only one left. This will be cancelled. And as a result, we're getting the function final answer as a function of r. So it's a q over 4 pi epsilon naught r to the power of 3. I'm just first collecting all the constants. And r. Okay, I wrote it on purpose this way because all these are constants and this is our variable. So it's growing linearly with r, electric field. And again, it's only correct when we are inside. So now let me frame it. And so the final step, let's just plot. Let's just plot this electric field, this function and this function, just to see overall the whole picture. So electric field versus r. I think when I remember in my entrance exams to the university, I was asked, I remember, to draw something like this. I remember they gave me a metal sphere and asked me to draw electric field, electric potential. And I remember also dielectric charge sphere also I was asked to do that. Okay, so let's assume that this is r capital, our surface of our charge sphere. And inside, constant times r. So it's a linear function. So in this region, we should have some linear function. Let me draw it. So proportional to r. Outside, again, it's a constant and r squared. So some kind of parabola. So proportional to 1 over r squared. So that's the electric field. Okay, so what else? We still have a few minutes. All right. So after the break, we will continue with, not continue, we will start cylindrical symmetry. And you know what? Before you go, let's ask. Okay, so this is the what I discussed with you, and this is again out inside. Let's discuss this question. So you can think it over the break, and then I will discuss. So we have case A and case B. In case A, we have a charge plus Q. So this is just a charge plus Q. This is Gaussian surface. Or we can say just the surface. Of course, we can say about the electric flux through this surface. In case B, there is a charge plus 2Q, and then this is the surface, just imaginary surface. We can say Gaussian surface, right? So we need to answer the question, flux through which surface is larger? Here, this surface of radius r, this surface is radius of 2r. So just the question is about which flux through which surface is larger. Okay, and you can have a break, and after the break we can discuss that. Okay, I think at the end of the previous class, you remember we discussed a bunch of questions. There were tons of surfaces and 3 charges, and we were answering the question, what was the amount of the electric flux through that or these or those surfaces, right? So you remember electric flux, essentially I told you, if you're interested in the electric flux, it depends only on the amount of charge within this or that surface, only, right? Of course, you can also calculate flux by integrating that, but integration will be more complicated. So of course, it's easier to see which charges are inside. So in this case, we just need to apply this for this surface and for that surface. So for the surface A, so the flux will be what? Flux will be Q divided by epsilon naught. Sorry, by epsilon naught. For surface B, the flux will be 2Q divided by epsilon naught. Okay, let me write it. So for the flux A, it's Q divided by epsilon naught. Flux B, 2Q divided by epsilon naught. Which one is larger? Of course, it's a silly question. Okay, not silly, but almost insulting question. Of course, yeah, flux through the surface B is larger. In this case, the size of the Gaussian surface does not matter. I can take this surface all the way to infinity. Flux will be still exactly the same, 2Q divided by epsilon naught. Or I could make it much smaller, right? So over here, right next to that charge, it will be still the same flux. It only depends on the amount of charge inside and divided by that universal constant. And what this surface I can make either huge or small, it doesn't matter. So flux will be exactly the same because we are not changing the amount of charge, right? So the source of electric field line stays the same, so flux will be constant, the same, right? So flux through surface B is the, probably I should have written that. I will change that next time and write something like that. Okay, so now, yes, I can see option A reduced significantly number of students who answered that. Right. Again, I'm not sort of judging your answers in terms of attendance and so on, as long as you participate, as long as you put your best effort, so that's what I want. Right? Okay, a few times I gave questions like this among multiple choice questions on the exams, right? And I think after this you shouldn't be having troubles with, right? Sort of, we discussed it first time in the previous class, and now one more time, usually after 2 cases. You should remember this. Right? Okay, so now back to new example. So this time, let's assume that we have an infinitely, okay, so pretty much what does it mean whenever you see in mathematical or problem of physics a long object? What does it mean physically? And infinitely long. Like I remember in one of the classical mechanics problems up on the graduate level, there was a problem. Let's assume there's a bottle oscillating in the bucket of water. no, in a large bucket of water. So what does it mean, large bucket with water? Essentially, it's an ocean, right? So pretty much it doesn't have any ends, right? So whenever you see large or long, it means essentially infinitely long, right? Infinitely large, right? Sort of. We need to read the language. Okay, so infinitely long cylinder. And of course, in this case, total charge is not given, because it's kind of difficult to distribute a finite amount of charge over infinitely long object, right? So every time density will go to 0. So in this case, volume charge density is given. In the previous example, the total charge was given. Now charge density is given, right? So rho. And radius of the cylinder is given. So this is our physical situation. And we need to find, again, electric field outside and inside. So let's start with part A. We need to find electric field outside. Of course, for R larger or equal than R capital. Again, wanted to say something and suddenly it flew out of my mind. Okay, anyway, so I will it will come back to me. All right. So we need to find electric field outside. Again, we have either we can apply Coulomb's law with a probe charge and do that type of integration. It's possible to do it in this case, but it will be significantly more complicated to find the electric field. So it's easier to use Gauss's law. Okay, so now let me again rewrite Gauss's law. E dot dA Q in over epsilon naught. And again, first step, of course, now we all know. The first step, we need to pick a Gaussian surface, right? A Gaussian surface. And again, we need to pick it in the region where we want to find the electric field. Sometimes I walk around during the final exam or the first midterm exam, and I can see sometimes students pick the wrong, the right surface, but in the wrong region, which is, of course, quite silly. Okay, so of course, our Gaussian surface must be outside. Again, you have universal freedom to pick any surface you want, closed surface you want. But of course, we need to pick the best one so we can solve the problem. And during the break, you actually started talking about that. So what can be used as a Gaussian surface? Most likely, again, in order to utilize the symmetry, the Gaussian surface must be another cylinder over larger radius, right? But over finite length. Over finite length. A length, we're going to just introduce some, L, length of L. Because at some point, that L will disappear. But that Gaussian surface will have a finite length. Okay, so now again, I will use green dash lines. Or should I use dash? You know what? No, it will be more complicated. I will use solid line. Okay, good enough for Friday. Wow, it's really, really, okay, good enough. It's more than art. I can say it's more than art. It's the way I see things, right? So don't judge me, right? If Malevich could sell a black square for millions of bucks, right? So I can sell this for the class. Okay, so over finite length L. Probably you don't know who Malevich was, right? So that famous painting, Black Square, you know, right? And of radius R small. Right? Again, it's essentially variable. So that's our Gaussian surface. Great, so the first step. Now, the shape of this surface is significantly more complicated than the shape of a sphere, right? Sphere, we had one type of surface, spherical surface. But our now this Gaussian surface consists of essentially two types of surfaces. Flat, cylindrical surface. So it makes sense, because we're going to start evaluating that integral, surface integral. It makes sense that we will split this surface into three surfaces. Surface 1, surface 2, surface 3. Right? In order to do integration, we need to split this integral into three surfaces. All right, so let me write it. E dot dA, right, equals to okay, let me label them. I think probably I will call this surface as 1, 2, 3. Yeah. So let me call this surface as S1, cylindrical wall, or that cylindrical surface. Then this front side or front facet, let me call it as S2, and this back facet somewhere over there, right, as S3. Three surfaces. It makes sense, because we're going to integrate over the surface, and we have three different types of surfaces. So we're going to split this integral into three. E dot dA plus S2 E dot dA, lots of writing, and of course the same for the surface number 3. Simple question, guys. Pure cosmetic question. Look, here we have an integration over the closed surface. So we have this circle. Why didn't I write over here circle, circle, and circle? Because by themselves, if you put together all these surfaces, of course they form a closed object. But by itself, this side, it's an open surface. By itself, this side is also an open surface. And by itself, the cylinder is also an open surface, right? So that's why over here, strictly speaking, from the mathematical point of view, we shouldn't be writing a circle in the middle of the integral. Right? Okay. You know what? I should have spread them a little bit more, because I'm planning to write something underneath. Okay, it doesn't matter. So let's start with surface number, okay, this second one. So, about this integral. And so let's again, like in the previous example, show on the picture area vectors and electric field vectors. Area vectors. For the cylindrical wall, what's the direction of area vector? Again, it must be towards the outside and must be perpendicular, so it will be radial. At any point, it will be radial direction. It will be along radial direction. So I can take, for example, here a small patch, and this will be my dA. No objections, right? Now, what about area integral, area vector for this, for example, S2 surface? Again, it must be perpendicular and towards the outside, right? And the same for S3. So area vector over here, if I take this patch, so this will be my dA. And for this patch over here, if I take some small patch, this will be dA. See that, right? Makes sense. Perpendicular towards the outside. Now, what about now electric field? What? Same direction as what? Areas. These. All of them?
For each one, there will be according to
Okay, so let me justify what will be the direction of the electric field also very quickly. Although by looking at the symmetry, you should be able to guess, right? So the direction, justify the direction of the electric field. So let's say this is our charged cylinder, right? And let's say I want to find the net direction of the net electric field at that point. Right, so let me draw auxiliary line. Right. And so now I can take, for example, here a small point charge. So contribution from that point charge to the net electric field at this point, it will be this. Then at the same time, I can find symmetrically positioned point charge over here. Because again, it's uniformly charged. I can find for any charge over there, I can find symmetrically positioned charge over there. And of course, contribution to the net electric field will be this. Exactly the same in magnitude, in absolute value, because this distance and this distance is the same. This I picked, and I picked the same charges on both sides. So if I add their contributions, the net electric field will be pure radial. Every time these horizontal components are going to cancel. During the integration, we are going to discuss each point, contribution from each point, and every time horizontal components are going to be canceled, giving us only radial components. So everywhere the electric field, actually from inside, will be something like this, right? At every point, radial direction, right? And that's what you were saying, right? Okay, so now, of course, I don't want to draw tons of these electric field lines. I'm going to just draw them next to our area vectors. Obviously, over here, it will be this way. And now, on this patch, what's the direction of the electric field relative to the dA? Because at this point, quite often students make mistakes, so that's why I'm sort of stopping and started bugging you. So what's the direction of the electric field relative to this area vector? Perpendicular, perpendicular, good. Because quite often, not quite often, some, not small number of students, at this point, they develop a habit of, it looks like electric field and area vector all the time parallel to each other, and then when they come to this point, they keep drawing it parallel. No. In this case, it's electric field is radial, area vector is horizontal, right? So it's a 90 degrees between these two vectors, right? So this will be my E, and this angle is 90 degrees. Thank you, right? So it's good, right? So be careful at this point, because it's a common place for mistakes. And over here, I can also draw similar picture again. Area vector and the electric field vector, they are perpendicular to each other. And of course, everywhere on each of these surfaces, right? Cool. Okay, so now let me then write explanations about this integral. So for the surface S2, actually, can you tell me immediately, even without integration, what's the value of the flux? Oh, I remember we discussed this question with you a couple of classes ago. I forgot. I think we discussed this question a few classes ago with you. Can you tell me what's the value of the electric flux through this surface S2, without calculations? Can you tell me the answer immediately? Yes, the right thinking, the right first word. It's a flux, it's a number of electric field lines crossing the surface, right? So based on that statement, so what will be the flux? The value of the flux? You know the answer, right? So, and okay, say it, and then I'll get back to. Is it 0? Okay, again, your explanation is more like mathematical. Conceptual, what a couple of classes ago you were not here, we discussed. So conceptually, it's what is flux? It's a number of electric field lines crossing the surface, right? But in our case, This is the surface S2, and electric field is parallel. So it physically cannot cross this surface, right? It's parallel. So pretty much if we ask, so how many lines crossing the surface, which is flux? Of course, 0, because they're essentially parallel. It's a conceptual explanation of the fact that the flux is 0. But of course, what you said, it's a mathematical, because in that case, angle is 90 degrees, cosine of 90 degrees, 0. Good luck with that, right? So, right. Okay, cool. And the same surface S3 is going to flux through the surface S3 will be also a 0 for the same reason. Right? But of course, I'm going to write here mathematical explanation. So E is perpendicular to dA. Okay, so this is related to that integral, perpendicular to dA. And of course, the dot product is 0. E dot dA equals to E dA times cosine of 90 degrees. And cosine of 90 degrees is 0. You see, cosine of 90 degrees. This is 0. So this second integral can be dumped. Bless you. So, and the same story with the S3. Again, I will write, so E is perpendicular to dA. And for the same reasons, okay, let me write, so the same. So it looks like only one integral will be left. And again, we can simplify it like in the previous example, because now E and dA are parallel. So let me also write underneath these explanations. So now E and dA are parallel. Right. And so the flux, not the flux, the dot product, E dot dA will be equal just E dA. Okay, I skipped cosine, but of course you understand theta equals to 0 degrees. Okay, so, and pretty much now you see the logic why we picked a cylindrical surface, because contribution from that side and this side will be 0, so which is great, right? So now this will be integral over the surface S1, but now it's just the product of magnitudes E dA. Right? This is 0, this is 0, and now instead of this dot product, we have just a product of magnitudes. Right? E dA. So, and now again, symmetry, we need to use the symmetry. And I will give you a very similar sort of explanations. Again, if you sit at this patch, and you, let's say you know the value of this electric field, let's say 5 newtons per coulombs, and you look down, you see that distribution of charges. So that distribution of charges gives you 5 newtons per coulombs. And then if you move yourself to, for example, this patch, again on the Gaussian surface, and if you look down, the distribution of charges will be exactly the same. You will never be able to see the difference. It immediately tells you that value of the electric field at that patch must be also 5 newtons per coulomb. Of course, direction is going to be different, but who cares about the direction, because now we have magnitudes only in our integral, right? Okay, so now I will again open my explanation box and I write electric field is constant on the Gaussian surface S1 on the, okay, of course it's a part of the Gaussian surface, but anyway, so let me write this way. Okay, it looks like I need to change my marker. It's getting too losing contrast. Wait, which one is the new one? Okay, this one. Okay, so if it's a constant, it can be extracted from the sign of integration, and we're going to get, all right, so E integral over the surface S1 dA. Right. Again, it feels sort of long because I'm trying to justify everything. But of course, without justification, it would take maybe a few minutes to finish this problem. And now, again, be careful, guys. What's the value of this integral? If you, yeah, usually I don't give the formulas like this. So what's the value of that integral? Area of this surface. So what's the what will be the formula for that area? Length L times what? Width. What do you mean by width? L length. Yeah, I agree. Okay, guys, if you are sort of confused a little bit by this, look, of course we all know how to find the area of the rectangle, A times B. But what if I take this and made a cylinder? Area is still the same. So it's still A times B. But now this is our A and B is the circumference. So it's a L times circumference. It's essentially what's the difference between rectangle and the cylinder? You just change the shape, right? So still the same A times B, right? So L times circumference, right, guys? Okay, cool. So it will be circumference. Okay, which R?
Big R. Small R, sorry. Big R.
I was ready to put my boxing gloves on. Physical education. 2 pi, I'm joking, of course, R times L. 2 pi R times L, right? Because again, careful, because I see on the exam quite often students just, without being careful, just grab whatever R closest. Right? So E times, I will just probably write it here underneath. E times 2 pi R n times L. Okay, so that's the flux, number of the electric field lines crossing the surface, right? Physical meaning. And so, according to the Gauss's law, that must be equal to Q enclosed over epsilon naught. And now, pretty much it's all the way, it's, we just need to find Q enclosed. The final step. Okay, not the final, but almost getting closer to the end. So, Q enclosed. And again, guys, it must be clear for you. In the previous example, total charge was given, and we had to find volume charge density, right? Now, rho is given because whenever I give a problem like this on one of the tests, right, I don't know, maybe 30% of students, or maybe slightly less, maybe 25, they try to find at this point volume charge density. It's given. Rho is given, so read the problem carefully, right? So you don't need to find rho. They start introducing Q capital, which is not given, start doing some funky moves, right? Not needed. Rho is given. I know, 5 coulombs per cubic meters, for example, right? So rho is given. So it means that, again, we need to use the same formula, which we used in the previous example. So it's a Q over V. So volume charge density, it's a charge divided by the volume over which that particular charge is distributed. You can use different charge. You can use the total charge. You can use smaller charge. But every time you need to divide it by the volume over which that particular charge is distributed. Right? So in our case, we need to find Q. So it's a rho times V. So Q enclosed will be rho, which is given, times V. Okay, now which V? Which V? I'm not putting subscript now. Okay, lowercase r. Okay, look. Let's see on the picture where our Q enclosed is, right? So, what do we have any charges between this surface and that surface? It's empty space. There is nothing. So charge is only over here, right? So let me use blue line. So our charges, enclosed charges, are over there only. So as a result, V with which subscript, he's already smiling, right? So now which subscript must be used next to this V? R capital, right? Because our charge is only in our physical cylinder. So R capital, right? Okay, great. And the volume of the cylinder, back to you now, the volume. So we discussed the area and now the volume of the whole thing. Again, L, definitely we start with L. You're overcomplicating things. So L definitely, right? And then you need to multiply it by the area, because now you need to find the volume. L times the area of the base. So which is pi r squared, right? Pi r capital squared, right? Because it's a, okay, cool. So it's rho times pi r capital squared. It's this area, right? It's pi r capital squared area of the base times L. That's it. Rho is given, R is given, L is not given. We introduced it in order to get through the solution nicely and smoothly. So of course at some point it will disappear, as I promised to you. But we need to introduce that. Okay, so now we just need to plug it over here and finish the problem. Okay, so now E times 2 pi r times L equals to Q enclosed. This is rho pi r squared times L divided by epsilon naught. Okay, now a few cancellations. Actually, nothing can be cancelled. No, except L. L, of course, must go, right? L doesn't belong here. And so as a result, E as a function of R now. Pi also can be cancelled. Yeah, pi can be cancelled also. So pi. So it will be equal to rho r squared 2 epsilon naught, pretty much all constants. First I combine. Right. So these two r will go downstairs. So, but r I will write separately. That's it. That's the function. And of course, that's for outside. So for r larger or equal than r capital. Again, as I said, typical mistakes. Students try to find rho. Wrong r's can be used, but everything is picture should be in front of your eyes, because without picture, it would be easier to make some really silly mistakes. Otherwise, it's quite straightforward. Again, as I said, I remember myself, we liked problems like this because once you get the idea, it's very mechanical almost. So now inside, final. So that was outside, and now let's find the electric field inside. So B. So electric field inside. So for R less or equal than R capital. Again, we need to start with the Gaussian surface. All right. You know what? I don't want to redraw the picture. I will just draw another Gaussian surface inside of that. So, okay, this time I will use dash line since it's definitely not visible. And again, of some finite length L, which is again not given. We just introduce it in order to get through the solution. Right. Of some arbitrary radius r small. So that's our Gaussian surface. And again, I can ask you, are we going to see any differences between this point and that point? It will be every symbol is going to be exactly the same, exactly not similar, exactly the same. So I will just write using exactly the same steps. So we will get to that final point, not the final, that intermediate point. So 2 pi RL equals to Q enclosed over epsilon naught. So now Q enclosed. So again, we need to see on the picture where that charge is. I feel like running out of colors, right, in order to highlight that part. Again, the total charge inside. So it's this. I will just use different line. That's the charge which we're interested in. Right. So again, charge density is given. So we need to find Q enclosed. We just need to charge density and multiply it by the volume over which that particular charge is distributed, that highlighted, doubly highlighted region. Right. So now it's a V with which subscript? Now it's a lowercase r. Now it's correct, right? Right, because it's this. Okay, let me even write. So it's a V with the lowercase r, right? So Q enclosed equals to rho times V with r small. So of course it will be volume. Now, again, it's a volume of this cylinder, right? L times pi r small squared, yeah. So it will be rho times pi r small squared times L. So that's our volume. Right. Okay, so now back to this expression. So we just need to plug it over here and finish the problem. So it will be E times 2 pi r L equals to rho pi r small squared L divided by epsilon naught. Oh, now there will be more cancellations, significantly larger number of cancellations. L, first of all, go as it should be. Its job is done, so now it can go. Now pi also goes, and 1r goes. Right. So now let me write over here. So the electric field as a function of r will be equal to rho over 2 epsilon naught. Yeah, that's the constants. Those are constants. Rho over 2 epsilon naught and times r. That's it. So that's the function. So again, let me plot it. Plot them, both functions, this and that. The final step, just to appreciate the beauty. All right, so that's the electric field. This is radius. This is surface of the cylinder. And of course, inside proportional to r. Again, these are constants. Inside, it's inversely proportional to r, so it decays as 1 over r. Right. So inside, it's growing linearly, and then it decays as 1 over r. And of course, matching, so you can get exactly the same value of the electric field from the outside or from inside. Both functions must match. Okay, any questions? But of course, guys, you need to practice by yourself these examples, right? So, because for you now it sounds, yeah, I can see, I understand, I can follow. But once you start writing by yourself without having anything in front of your eyes, only at that point you will start realizing what is still missing in your head. Because it's not just my advice, and you can ask anyone and everyone will tell you. You need to do everything with your own hands, otherwise there will be still some misunderstanding in your head. You know what? We still have a few, okay, actually 7 minutes, great. There is another example in my slides. I will, which is, yeah, you can see. But I want to discuss it. I want to discuss it, and then you can read by yourself. What if we have this situation? So it's a new bullet. What if we have a sphere? Okay, it's a first example, essentially, modified. It's not cylinder or nothing like that, so we're done. Any questions about that example in particular? Okay, cool. All right, so now what if we have this sphere, charged sphere, let's say of outer radius A, and then let's say inside there is a hole of radius B. So charges are actually over there. Okay, over here. So that is just hole. Let me write, it's a hole. And let's say we know that the total charge is uniformly distributed and the total charge is Q. So first of all, how can we find volume charge density? So what if we want to find rho? Again, by definition, it's a Q divided by the volume over which that particular Q is distributed. We have this Q is distributed where? Between these spheres, right? So in this volume. So pretty much it's we need to take the total charge Q, and so how can we get that volume? Essentially it's a sphere with radius B minus volume of the sphere, A, minus sphere with radius B. So it's essentially VA minus VB. Bless you. It's not B minus A to the power of 3. No, it's a volume minus volume. So it will be a difference of volumes. So it's a V with radius A minus volume with radius B. Right? Of course, I will give you, as I said, I created an assignment where I created a bunch of different situations where you have to just look at the geometry and make the decision. But again, it's all about this, or maybe a two-dimensional situation. Q over 4 pi over 3 A cube minus B cube. It's not A minus B to the power of 3 because I see it quite often, right? So cube of difference is not equal to the difference of cubes. So we're subtracting volumes. So that's the story, right? And let's say, for example, we want to find the amount of charge in the Gaussian surface. Let's say this is the Gaussian surface. So now, what do we have to do? We found volume charge density, and now we need to multiply again from this formula. Now we need to find the amount of charge in this region. So that Q enclosed will be rho, which we found, times the volume over which this particular Q enclosed is distributed. So it's a volume of this object between, okay, this is radius r small. So now, in this case, Q enclosed will be rho, that rho, times the volume. What? How can we get the volume of this object? It's the volume of the sphere with radius r small minus volume of the sphere with radius b. So every time we need to subtract the whole, because in the whole there is nothing. There is nothing. It's empty. So it's a volume of the radius r minus volume of the radius b. Of course, you can just write explicitly everything. And okay, there's another problem, but I will just send you by email or attach to the Blackboard. Just simple. All right. So it's Friday, and we still have a couple of minutes. So we can make it short.